All right, for those of you students that missed class due to debate or cross country or due to illness, I'm just going to go over gas laws. So over the past 2 weeks, we've been looking at various relationships between variables with gases. So we're going to put that all together now and actually derive a gas law from this. So it's like a truth about gases. So first of all, we figured out already that the relationship between pressure and volume is actually an inverse relationship. So it's inversely proportional. When we drew this as a graph, it actually made a logarithmic graph where we saw that if we increased something by 10, whether that's pressure or volume, the other one actually decreased by 1/10 of the value. So because this is logarithmic, and we could say the same thing about 2, and then this was 1/2 less, then that's actually going to give us a graph that looks in this like logarithmic fashion. Mathematically, we said that this was the right formula for this, and this was correct, to give that inversely proportional relationship. Now, in the lab that we just did this week, we saw that the relationship between pressure and moles, which we represent again with this variable n, was directly proportional. And moles are a unit that we're not, with which we're not as much, we don't have as much familiarity. So moles are actually a unit that help us measure how many particles are in something. How this would actually look graphically, this would be a direct relationship. So as we increase one, the other one is going to increase in a proportional fashion. So we would just end up with like an even slope. Mathematically, if we're doing that same thing, we would have pressure, again, pressure being P, over N1 equals P2 over N2. So that would allow us to increase both. Like if we do the 10 thing, like if these are 10 to start with, if we increase the pressure to 20, the moles would increase to 20 as well. Now, these don't have to be equal values. The actual overall what it simplifies to has to be the same though. Now, in your gizmo, you were exploring the relationship between pressure and temperature, and what you should have found in doing that this was, again, directly proportional. So the graph for this relationship would actually, again, look pretty much like that. Mathematically, oops, sorry about that. Mathematically, this is going to look very much like our pressure in moles formula, but this time we'll say, hey, we're going to use T for temperature. Now, notice in all three of these, we've got a P. So we actually use pressure as kind of our base unit to figure out how are all of these other things related. So from this, we can actually derive all of these together to make something called the combined gas law, which actually tells us the relationship between all four variables kind of at the same time. So if we derive all of that together, we would do our pressure and volume together. So P1, V1, just like we had up here with our pressure and volume relationship. And then we notice we have both moles and temperature on the bottom. And I feel like I'm writing that in a way that looks like those are I's, but those are both just ones. So that means P2, V2 would be equal to T2, N2. So what this actually can tell us is when we have temperature and moles, that's also going to derive that relationship as well. So based on this, these are going to be inversely proportional based on the actual formula. Temperature and pressure, since we have on top of each other, even though we never mathematically tested that, we did see that in the gizmo. We know that those are directly related. And then similarly, we never actually tested temperature and volume, but it makes sense to us that those would be directly proportional because we know as we heat up gases, they move further apart. Okay, so that makes sense. Now, what are we going to do with this? Well, it's a formula, and we can actually use it to do mathematical calculations. So in order to do this, we've been learning about units. There are some important units. The first thing is whenever we have a temperature, it must be in Kelvin. So as a reminder, to convert from degrees Celsius to Kelvin, you take whatever the degrees Celsius is and you add 273.15, and that will give you Kelvin. One thing to note when you're writing Kelvin, you just write K. You don't write a degree symbol like we do with Celsius. So you're going to have to do this pretty frequently because in lab we actually take units in degrees Celsius because we don't have a Kelvin thermometer. So you're going to have to do conversions. Generally, the unit you have to use for volume as well as liters. So you may have to do conversions to make that happen. And sometimes you'll see this little STP thing. That means standard temperature and pressure, and there are certain conditions that go with that. So standard pressure is going to be any of those equivalent conversion factors that we already learned about. So you can kind of pick your unit that you would like to use. In that case, kPa is slightly more preferred just because that's generally what people use. So when in doubt, if you have to pick, you can pick kPa. And then temperature, the standard temperature is actually 0 degrees Celsius, which is 273.15 Kelvin. So if it just says STP in the problem, this is what it's actually asking you for. It's saying, okay, that means the temperature is 273.15 K and that the pressure is going to be the equivalency unit. So in that case, you can either pick or just say, okay, I'm going to use kPa. So overall, we've got our combined gas law, and then in terms of how we actually are going to use this, again, we need to make sure everything's in Kelvin and liters, so we have to use conversions like we've been doing. Now, what we're going to do is do a couple of problems together, and then you're going to be working through the rest of these on your own. In order to help us actually think through these 4 variables, one thing that I always will want you to do, is, especially if I don't even give it to you, is use a PTVN table. And all this is a place for us to organize what variables we actually have and to figure out how they are changing. This is going to help us make predictions and check our answers at the end. So if we look at our first problem here, it says a gas occupies a volume. So we already can see we have a variable V at a certain temperature, another variable, and a pressure. So this one looks like it has 3 different things in it. In this case, they want to know the volume. So we're looking for volume of the gas at, there's that STP thing I mentioned. So that tells us that our temperature is equal to 273.15. Okay. In that case, in our pressure, hey, guess what? This is in kPa, so let's just use the same unit so we don't have to convert. That means we're going to use our pressure being 101.325 kPa. Now, the only real decision you need to make at this point is, are these V1, T1, or P2, T2? Now, generally what you do have to pay attention to how they're describing it in the problem, but generally those first things given are going to be just your first things. So we would say volume 1, temperature 1, pressure 1. You do have to make sure all those things match up, because sometimes they may say the volume was this and then it changed to this, or the volume is this, but initially it was this. So you do have to pay attention to what the problem actually says. In this case, though, it says it's occupying this volume. We want to know what it's going to be if the conditions were changed to STP. So that means these are going to be our ending or second volume, temperature, and pressure. So our initial pressure, we have one, it's 215 kPa. Our final, we have that as well. It's 101.325 kPa. And again, I chose kPa so that our units would match and I would not have to do any conversions. Now, our final temperature, we know is 273.15 K. But now we run into a problem. Our temperature is initially in degrees Celsius. So in that case, I need to do a quick math conversion. I'm going to take 19.5 degrees Celsius plus 273.15, and that's going to give me my Kelvin. Okay, when we do that with just some quick math, that's going to be 292.65 Kelvin. 65 Kelvin. But you should still consider sig figs. So since this is our least decimal place, this would be 292.7 Kelvin. That's the number that we're going to write in up here on our temperature. So 292.7 K. Make that clear. Now, volume, our initial, or V1, in this case is 25.2 milliliters. Again, guess what? We need it to be in liters, so you're just going to do a quick conversion. So 25.2 milliliters, our conversion there. 1 liter is always 1,000 milliliters. So you're going to divide 25.2 by 1,000. When you do that, it will move the decimal place 3 times. So we're going to end up with 0.252 liters. So that is our initial volume. Our final volume, we don't know. So we'll put a question mark. Moles, we're not dealing with that in this problem. So if we look at this, we can make a prediction now before we do any kind of math. And we can say, all right, our pressure actually decreased. So the effect of the pressure is it's declining. Our temperature also declined, which guess what? That makes sense because pressure and temperature were directly related. Now, we know that volume from looking at our relationships up here is going to have an opposite relationship with pressure, or an inverse one. So we would expect our volume actually to increase if the pressure and temperature are declining. So that's our prediction. The volume is going to increase, again, based on those relationships. So before we do any kind of real math, yes, we did some conversions, but we have to make sure that we've predicted all of that. Now, what you're going to do is you've got one of kind of two ways you can deal with this, but the main way at this point is we're going to plug in our variables, and again, our equation, our combined Laplace law. This is the overall equation, but at any point, like we're not using moles here, you can actually just be like, okay, I'm not using moles, then that's my equation. So we'll plug in pressure, which is 215 kPa, times our volume, which is 0.0252. And I think you can see now why having these little tables are really helpful, because we've now organized everything. And we're going to make that equal to our, again, final pressure, so 101.325 kPa, 273.15. Oops, no, I'm putting that in the wrong spot. I'm just looking at the table and not putting anything down where it belongs. Okay, so 273.15K, and then we're looking for V2. Sometimes what can help is if you actually just rewrite it without the variable, especially since this is the first time we're kind of using this. And if I had actually done that, I would have been thinking more carefully, and I would have put my temperature in the right spot. So at this point, you just have to actually divide everything out. And I'm going to do this in just a second. I'm going to pause it, write the answer for you, and then we'll talk about how we deal with sig figs. Okay, so I did all the math and I did everything in my calculator. So what I actually did was multiply the initial volume by the initial pressure, divide by our initial temperature. Then I'd instill in my calculator, multiplied by the second temperature, and then divided by the final pressure. I did all this in my calculator so that I would not lose any precision along the way. And since this was all multiplying and dividing, the rule is the same. And at the end now, I've got like my unrounded calculator answer. Now I'm going to round to sig figs. If I look at this, my least number of sig figs, I have the same least number in the initial pressure and initial volume, which is 3 sig figs. So my final answer down here that I'm going to circle needs to have 3 sig figs as well. And this is pretty easy to do because it's just going to be 499. So final answer there is 0.0499 liters, and guess what? That matched our prediction, so we knew that we did it correctly.